Jupyter notebook. And I will go to the next session, which is using GPUs with Python. So GPUs are a type of hardware that can be used to accelerate our simulations. So this is how a standard node looks like on Kebnekaise. So a standard node includes some number of cores. In this picture, it shows that the node contains 14 plus 14 equal to 28 cores. Right? So here you can distribute your Python code and use these 14 cores to perform your parallelization. So this is a standard node, right? And here is how a GPU accelerator, GPU card looks like. So in this case, you have many more cores. So previously we saw there are 28 in a standard node, but here each of these squares is essentially a lightweight core, right? So, and your code can be in principle parallelized to use all these cores. But the code needs to be highly parallelizable, right? So not all the codes are suitable for this architecture. Especially, for instance, the linear algebra operations are suitable for using this architecture because they have plenty of operations that can be distributed across these lightweight cores. So in a standard node, this is the situation in different clusters. And this is the case in the Kebnekaise cluster. So there are some GPU cards attached to the sockets, and these constitute one node with a GPU card on Kebnekaise. So this picture was for the K80 GPU cards that are now retired. They are not present. We have now on Kebnekaise the B100 GPU cards and also one AMD AMI 100 card. But architecture here or the layout, it's similar. So these are two quantities that I wrote here that can be used to characterize the performance of a CPU and a GPU. And if you dig into the information of GPUs, you will find them. They are called latency and throughput. So the definition of latency is the time spent in a unique computation, right? As for instance, if you are solving a scalar operation. And throughput denotes the number of computations that can be performed in parallel. So by using this, we can characterize the CPU, and we can say that the CPU has low latency, which is because it is able to do really fast computations, but also low throughput because only a few computations can be done simultaneously. So as we saw before in a standard node on Kebnekaise, if we consider several cores, we can do up to 28 computations. Now, in the case of the GPUs, the latency is high, and the throughput is also high. So because in the case of the GPUs, there are many more cores, right, that can be used to do the parallelization. So schematically, it looks like this. So in the case of the CPU, we can have only a few uh, high-speed cars, right? But in the GPU, we can have many more cars, but they are slower or much slower than those. So now every Python program is suitable for GPU accelerator, and so unfortunately, right? So some codes can be highly parallelized and they are suitable for that, but not all of them. Linear algebra operation, yes, they can be done. So here I wrote that many Python packages are not CUDA aware, but some have been written uh, to use GPUs. So for instance, NumPy and SciPy could use GPUs by using some additional module like QPy. Numba, the module that we saw before, has some features that let you use the CUDA code that can run on the GPUs. So this is what we will do here with the Numba example. And so here there is something that needs to be done before running the CUDA code. Let me see. Yeah, so you need to load these modules. The Python version is different than the one we used before. And also we need the OpenMPI, right? And we need to do some installation. So I can do it here. So first of all, because I loaded some modules previously, I will do a more module purge. Then I will load these modules here. And I will create an environment. Let me see. Actually, I have already the environment because it can take some time. And I will just source it. Okay. So then we can install Numba. Yeah. And I hope I installed it previously because it can take some time. Yeah, it's there. So otherwise it takes the order of 1-2 minutes, right? And now that we have uh, Numba installed, we can use a simple example Add it is here. It's a add list, adding to a list of elements. We will use here the function for the CPU here. This is something that you would write if you do the serial addition of these two lists, or if you do the GPU function, then you can use a decorator from the Numba module called vectorized, and define the target, which is for CUDA. And here is what you will compute, this summation. So, okay, so all this is here. Yeah, it's here. But the target is... So this is essentially the same function as it is here. And now we can run this. As we did before. Let me see. So notice here that I am using the srun command as I did before. And here I will specify N1, yes. And I need to specify the name of the GPU card. And the number of engines that I will use. In this case, it's just one. The time is 5 minutes. So depending on the time, it can take some time to get it running. So when it runs, you will see the results, and it will tell you the time that it took in the CPU and also in the GPU part. So we ran this previously, as you can see here. So for longer jobs, it's better to use the batch scripts that we have been mentioning. And this is how the batch script looks like. So here there is an exercise that we included for the integration 2D, but now with the Numba module. Is there any questions at this point? So if that is not the case, then you can try this exercise until 250, and let me know if you have some doubts or questions about this. So I will stop sharing here.